Hello everyone, my name is Aurela Qamili. I'm part of the engineering department at Albanian University and a PhD student in the Polytechnic University of Tirana. I study material science and my focus is electrical and mechanical properties of polymeric composite. Today I will be presenting my work titled Optimization Driven Energy Modeling of Polypyrrole-Coated IoT Sensor Networks for 6G enabled smart buildings. Smart buildings are increasingly relying on dense IoT sensor networks. These sensors can monitor indoor conditions, structural behavior, energy usage, and also safety related parameters. With the development of 6G, these monitoring systems are expected to become more connected, more intelligent, and more responsive. But however, a main limitation remains. Most sensor nodes are battery powered, so they need to operate for long periods without frequent maintenance. And for this reason, energy efficient communication becomes very important. If energy is not managed properly, the network can lose monitoring coverage very early. The main problem is that direct transmission consumes a lot of energy, especially for nodes located very far from the base station. And these nodes die very early and the monitoring area loses coverage quickly. Clustering is a common solution because it reduces long-distance communication, but instead of every node sending data directly to the base station, nodes send data to cluster heads, and cluster heads forward the data to, to the other heads. At the same time, polypyrrole-coated sensors can provide a material level improvement. Polypyrrole is a conductive polymer that can be used as a coating layer on existing sensors, so we don't need to produce new one. We just need to modify existing ones. The gap is that most studies treat these two directions in a separate way. So clustering as a model or material optimization as a model. The idea of this work is the combination of both. Communication technique plus material optimization at the same time. In the proposed work, conventional IoT sensors are treated as a reusable platforms. So instead of replacing the whole sensor, a thin polypyrrole conductive coating is considered in the sensing area. While in the network level, clustering is used to reduce long-distance communication. Not considered a specific clustering technique like Leech or others, which of course provide even better performance. I have chosen to focus only on the idea of the technique, so the theoretical basic one, in order to show that clustering plus material combination is better than just clustering alone. The proposed approach combines both of them, and this supports longer monitoring lifetime, better energy efficiency, and also circular economy principles, because existing sensors can be upgraded instead of just throwing them away and replacing with others. The simulation was developed with MATLAB. The model network contains 100 sensor nodes distributed within a 500 by 500 meter monitoring area, and the base station is located at the center, as shown here in the figure with the star, in order to optimize the communication. Each sensor node starts with 1 joule of energy as initial, and each transmission uses a 4,000 bit packet. The simulation runs for 1,000 communication rounds. The node deployment is fixed, so the results are also reproducible. And it's important because if the node position changes randomly over time, the results can also change. Using the same deployment allows fair comparison between direct transmission clustering and clustering plus polypyrrole-coated sensors. However, it has to be considered the fact that the nodes can move and are not always at the same time. So for a second round, other simulations will be performed considering that the nodes are not deployed always at the same way. In this work, a simplified first-order radio energy model was used. The transmission energy depends on the packet size and the communication distance, and the reception energy depends mainly on the packet size and the electronics energy used by the device. The polypyrrole coating is included in the model through a transmission energy reduction factor, and this does not mean, however, that polypyrrole is treated as a fixed universal value. It was modeled as a coefficient that vary within 0 and 30% energy reduction as reported from literature. As you can see from the table, the main lifetime metrics measured are first node death, half nodes alive, and last node death. In direct transmission, the first node dies at around 21, and half of the nodes are inactive by around 52. So we can see that direct transmission uh, loses usable monitoring coverage very early. With clustering, we have, of course, an enhancement. We have an improvement to around 78 for first node died, and half node dies alive, sorry, improves to around 1059. When polypyrrole is used as coating together with clustering, the performance improves further. First node death increases to 96, half node alive reaches 200, meaning that the coating gives the best usable monitoring lifetime. Even though last node death is greater than 1000, this is not the most meaningful result because only few nodes remain alive while most of the network is already dead, so it's lost. The efficiency, as I said, is evaluated within the range of 0 to 30%. Different studies report different values, but within this range, so I performed this as a parametric study in order to evaluate the result for each. The most important result is the first node death and half node alive, improving as the polypyrrole energy reduction coefficient increases, while first node death increases from 76 to 109 rounds. AGN, so half node line, increases from 168 to 223 rounds. This means that the coating mainly improves the stable and usable operating period of the network. Last node death it's moving, so it fluctuates between values because it depends on the few last isolated nodes. So it depends how many nodes are alive and near. So it is less reliable in this case as a metric. Uh, in what we have to say, this work shows that clustering improves network lifetime compared with direct transmission, and the coating improves it even further. The main contribution is the combination of network level energy optimization with material level enhancement, modifying directly the sensing state of the sensor. And this is also relevant to 6G enabled smart buildings. Regarding also my work with the cost action number CA22168 named 6G physical layer security. The current model is simulation based and uses a simplified radio energy model. So in the future, I plan to extend it with more realistic propagation conditions, steepen the idle energy, and also multi-gate layouts and considering the movement. So if the sensor node is moving from one point to another point, meaning that also the energy and the communication pattern has to change. Thank you very much for the attention, and please, if you have any questions, send me an email and I will be very happy to respond. Thank you very much.